Hello, everyone. First of all, I want to thank everyone attending this webinar, which will be an overview of all the solutions, instruments, test systems, software, and simulation capability that Chroma has to offer. Subsequent seminars will be an in-depth look of several of these solutions, and we will have these for the next 3 weeks, and you can also register and attend. The purpose of this webinar is to show you the breadth of products that we have, the breadth of solutions that we can offer you, from testing, simulation, application development, etc. A little bit about me. My name is Luis Velez. I'm the Director of AT Sales for Chroma. I've been with the company for the last 18 years. I started on the technical end of our business, so test engineer, senior test engineer, then test engineering manager. Eventually, I moved on to technical sales, covering a specific region for Chroma. Then moved on to the AT sales position, which is where we integrate a full test system, including application, software development, fixturing, etc. I hope you are doing well, as well as your families. Here at Chroma, we wish you good health and stay safe. Okay, let's get started. As part of the EV power components, a total testing solution from the EVSE to the battery webinar, we are going to overview all the different solutions to test, simulate an EV from the outside going in. We're going to start with the EVSE, which is commonly used as the charging station, along with all its types and all the different levels. Then moving on to wireless charging, and finishing the charging topic with a compatibility test system. The first item that we're going to cover inside the vehicle, it's going to be the OBC, or onboard charger, which, like its name states, charges the battery inside the vehicle. Moving along inside the vehicle, we're going to move to the next major component, which is the motor stator test system. After that, we're going to be reviewing all the DC to DC converters to lower the voltage from the battery or bucket down to all components like the entertainment system, lights, wipers, AC, blinkers, etc. After DC to DC converters, the next major component before getting to the actual battery is the BMS, or battery management system, that allows the battery to operate appropriately while reporting and measuring voltage, current levels, status, etc. After tackling that subject, we move on to the actual battery pack test system, then diving into the modules all the way down to the cell for both testing and simulation of each one. Lastly, which is often forgotten, but it does not make it less important, is the electrical safety of the vehicle, as well as the battery cells. We will overview 2 different tests that will allow you to safely test your battery cells before making them into a module, then into a pack, because you don't want to have bad cells or unsafe cells now or in the future. To tie all the previous topics, we will review the different types of software platforms that we can offer, from R&D or research and development to real-time environment, design verification testing, end-of-line or full production testing. I just hope this presentation is clear, as well as informative to everyone. The first topic is going to be EVSE, or charging stations, and their test systems. Our systems are specifically designed to test all available EVSEs out in the market. They're commonly known as charging stations, like I mentioned before, and we can test all charging levels, which is AC level 1, AC level 2, and the last one is DC fast charging, as well as covering all the major communication interfaces and the standard protocols between the EV and the EVSE. The communication types and standards are dependent on the region when they're being deployed. So power levels are the same. Connectors communication are different. Fortunately, Chroma has all the necessary instrumentation, software platform, and application development to either help you design your own, verify if you buy a charging station from someone, or test your own EVSE. One thing that I forgot to mention, I'm sorry, I was looking at the chat. I'm going to have my AT sales manager, Jeremy Block, responding to all chat questions. So any questions that you have in regards to this presentation, he can answer them. And the first question was, are we going to provide these slides? Yes, we can provide these slides after the presentation is done. So in regards to the communication interfaces and standards, we have the CAN communication, which is mainly China with all the GBT standards, and we already have all that application development done. PLC or power line communication, that's for the US and Europe or the European Union. For SAE, IEC, ISO, DIN. And when you go into Japan, we also have CAN communication for SAE and CHAdeMO. Like I mentioned on the previous screen, the connectors are level and region dependent. So here are the different charging interfaces available worldwide, which they can be roughly divided into four regions. We have North America, Japan, European Union, China, and then you have AC, both level 1 and 2, and DC fast charging. And then we have a specialty connector used by Tesla. So depending on your region, that's going to be the connector that you want to utilize on your car. Now, for the test system features specifically for level 1 and level 2, again, just to remind you, level 1 and level 2 are AC. So, as you can see on the screen, we have the gun, we have the charging station, and then we have the grid. The key AT components for this type of tester is going to be a grid simulator that will basically simulate the wall power, right? Then we're going to have our AC, EVSE box for GP, SAE, and IEC. That handles all the communication going back and forth between the charging station and simulating the car. And then we have an AC load, right? As you know, we have AC coming in from the charger, AC coming out of the gun, and then we're simulating the car with an AC load. The type of test that we can run under SAE and GB is the control pilot signal. As some of you may know, control pilot signal, it's a voltage level that we're going to be detecting. And it's going to be different states. State A, it's going to be disconnected. State B is going to be connected, but not ready to charge. C is going to be connected, ready to charge, etc. And each one, it has different voltage levels that you need to test for. We can also test for an abnormal control pilot signal. Let's say that a voltage is out of range. We can also do that and see how the EVSE responds to it. What's the current capacity for the EVSE? It could be level 1, level 2, and just push it to its max. If you're in the middle of a test and you disconnect the coupler or the gun, we can also test that. And also, I didn't put as a major component, but just basically using a scope, you can see the timing between charging and disconnect and how long it takes for it to be in a safe state. The energy transfer, again, timing test from where you plug the unit, it's ready to go, or it goes into the right state until it starts charging. You need to meet all the requirements for the standards. It's a timing test. We'll already have that test written for you. Harmonic distortion immunity. Again, these chargers are going to be in Europe. They could be in South America, European Union, US, Canada, etc. Right? So we'll be able to simulate all the grid and the different harmonic components that each country has. Because, you know, I mean, if you measure at your house and at your work, the voltage is going to be different, right? Even though both of them should be at 120. So we have the ability to simulate that, as well as doing any voltage interruption or dips, right? Let's say that you have a level 1, you're at your house, you turn on your dryer, your hair dryer, and also a vacuum cleaner at the same time. So you're going to have an inrush, you're going to have a voltage dip. You want to make sure that your charger not only protects the car, but also doesn't change its regulation for the voltage. And then if you have an invalid EVSE, right? It has the right connector, but it doesn't have the right communication, or you have one type of car and the EVSE, even though it matches on the gun, it doesn't have the right communication for it. So all those steps we already have in pre-written, ready to go. They can be used on R&D, design verification testing, production testing, etc. Now, for DC fast charging, the main difference between an AC level 1, 2 versus a DC fast charger, mainly it's going to be the output of the gun. It's going to be AC versus DC. One key point is that you have the onboard charger on AC level 1 and 2 inside the car. You have the charger inside the DC fast charger, and you go straight into the battery. So again, you want to have a grid simulator to be able to simulate all the input, different conditions, line regulation, peaks, sags, surges, inrush, power factor, etc. Then you have the DC EVSE for either CHAdeMO or CCS, right? And that's going to be the communication from the car to the DC fast charger. And then we use a battery simulator to make sure that the unit can take the power, and we're simulating the EV after we plug it into our box. Now, for a wireless charger test system, these chargers can be embedded in the ground at parking lots, roads, at your house. They're fairly convenient since you just drive over them, right? While being safe and flexible with having to deal with an actual gun or having to open the cap of your car, right? Because, I mean, eventually those will wear out, etc. These wireless chargers are both waterproof and weatherproof and still provide high efficiency for charging your car. We have identified 3 different types of wireless chargers. It's residential or your home. Motion, eventually we'll have the technology where part of the road is going to be a wireless charger. You can just drive in a specific lane and it'll charge your car while you go at it, or public parking, right? Outside in the city. There are 2 different types of modes. We have stationary and dynamic. The main difference is the car is moving, the car is not moving. So the car's not moving, stationary. The car's moving, obviously, it's going to be dynamic charging. We have standard tests for SAE and QCT, right? Again, we're looking at the grid, simulating it, and it's going to be the current, power factor, just to make sure that what's coming into the charger, the wireless charger, is the right voltage, current, power, etc. When nothing's parked on top of the charger, what's going to be the power consumption? But that's important because you don't want to not be efficient and still try to charge something that's not there. Cycle dropouts, again, if the grid eventually drops a cycle, you don't want your wireless charger to just shut off, right? Because, I mean, that could be pretty bad if we're talking about a motion type wireless charger. Harmonic distortion, power line disturbance, noise, etc. And then we just go into different protection tests. Now, the last 3 that I want to talk about is the magnetic field. It has to meet a certain standard because you're going to have a coil, you're going to have the car on top of it, and the magnetic field has to be within certain range and parameters. Also, the surface temperature, you have the coil, you have cement or whatever you have on top of it, right? And it has to be within certain temperature. And also object detection, right? Since the coil is going to be conducing energy, the cement will transmit that energy upwards. So it's going to be basically warm around that spot. one thing that you want to make sure is that you don't have, before you park, it goes into safe mode where if you have an object, it could be a rock, it could be a pet, for example, because again, cats like heat, and actually that's where it all came from. Cats like heat. You have a charger where it's warm, and you're going to have a cat on top of it. So if there's a transmission delay between the charger and the car, then it's just going to shut off because you don't want to harm any objects or animals or people. Now, the key AT components, again, you have your grid simulator, then you have your battery simulator, because if you want to simulate the car, and the XYZ platform. Again, it's not going to be exactly at 0 degrees on a horizon. You may have some gap because of the concrete, the way it was poured. So again, you're going to simulate the grid, you're going to simulate the platform, how it's sitting, and it could be the battery inside the vehicle, or it can also be the EV, the actual EV, and we removed the battery simulator because we already have the battery inside the car. So those are the main components. Again, we have ancillary components, which is going to be the software, the application, DMM, oscilloscope, etc. Now, we've talked about all the different types of EVSEs, right, or charging stations, level 1, level 2, DC fast charging, etc. Then we have different regions that these chargers can go into: Asia, Japan, European Union, US, etc. So you want to make sure that you have a compatibility test for your charger, right? And it could be either the car or it could be the charging station. Now, you want to make sure that you already have the right current flowing from the EVSE to the car, or the car is taking the right current. If you have a proximity circuit, we can also test that. Same thing, harmonic distortion. If it's, for example, a charging station, that it could be either level 1 or level 2, and it switches automatically between level 1 and level 2 for 120 or 208. We can also test for that. If you have an invalid test, let's say it doesn't have the right communication, you're trying to test a US type charger with PLC, but the PLC communication, it's not the right one, right? Or it has CAN communication that it's supposed to be for Japan or European Union. And then we have a list of available test standards that we can test to. So just to narrow it down, we went from the EVSEs, right? All the different levels, the communication boxes that we have to be able to test it inside the car, right? Whether it's AC EVSE or DC EVSE. We can simulate the battery inside the car, communication, we can simulate the grid. So now the UUT or the middle part is going to be the actual charging station. Now, if we go to the car and we start simulating the EVSE, the box, it's going to be the same, right? The communication box. The grid is going to be the same. Now we don't have a battery simulator because now we have an actual car, and we can test the car to all the different standards for J72, CNS, DIN, SAE, etc. So from that box that you can see on the screen, we can test either side, whether it's a car or it's going to be the EVSE, depending on the type of test that you're looking for. Now, let's go inside the car. The first component that we're going to look into inside the car is the onboard charger, right? The onboard charger, like I mentioned before, it's going to be charging the battery, and it has an AC input. For AC input, we only have level 1 and level 2, right? We have different communication interfaces. Again, it's going to be the same ones that we talked about before. So now you're going to have the onboard charger inside the car. We're going to be simulating the EVSE, the communication to it, right? And then we're going to be simulating on the other end the actual battery. So on this slide, you can see that we have a generic onboard charger. Again, the grid simulator is going to be acting as the actual EVSE. We have an OBC control box. Depending on the communication that we're going to be using, it's again going to be AC EVSE, DC EVSE, and then we have a battery simulator. Okay. The standard tests that we already have available for you are campus read and write, PLC. Again, it depends on the standard that you're testing to. Line regulation, which is from the EVSE to make sure that it's within a range. So let's say it's between, 85 to 105%, and it still should operate. So we can simulate that going into the EVSE, overcurrent protection, again, under voltage, over voltage, etc. Inverse current, the accuracy of the onboard charger, because again, you have a battery that you have to be able to charge or discharge, to charge at a certain level, right? So we want to make sure that at a certain charging current, we are within range. Rippling noise, timing test, peak current, etc. So from the onboard charger, we can now move to the motor stator test system. This test system is highly custom, right? I only have one slide for it because it depends on your motor size. It's going to depend on the type of test that you want to run. But as a quick overview, we integrate several of our instruments, like a one component tester, right? Which is an analyzer. It has AC and DC high pot, IR, which is insulation resistance measurement, a 4-terminal DC resistance measurement, and we have up to 10 ports for scanning, right? We also have an LCR meter to measure LS over Q and the winding space measurement, plus a vacuum system and a test fixture. Now, for the vacuum system, as you can read on the left-hand side, what we do is with the vacuum system, I'm sorry, we put the motor in the vacuum. We lower the high pot voltage on it, right? And that helps you with the gas discharge where you would have an issue. So it makes it safer, right? And it allows you to look into which winding you had an issue on. Because typically what you do is you just do a high pot and see if you have a short, you measure leakage current possibly, an LCR meter, and that's it. But you will not be able to find a fault or find a defect and be able to fix it, right? So with this test system, that's the importance of it. And since we're using a lower voltage under a vacuum, it allows you to identify the problem, fix it, instead of discarding your whole product. Again, if you have any specific questions in regards to any of the test systems, in regards to the standards, the components, software application, etc., please send it to chat. And at the end, between Jeremy and myself, we'll be addressing your questions either at that moment or we'll send it via email back to you. Now, the next component is the DC to DC converter. Their basic functionality is to ensure that the energy flow between the high voltage battery and the low voltage necessary inside the vehicle, it's there. Whether it's your stereo, your lights, your blinkers, headlights, etc., right? And there are two different types, whether they're a single direction or bidirectional, right? Using DC to DC converters inside a vehicle, it enables you to have scalable power variation and high modularity, right? So instead of having just one big module that takes your battery voltage and then distributes it from one unit, you can have multiple DC to AC converters. Let's say you need 12 volts, you need 48 volts, 24 volts. In some cases, you need higher power, lower power. They will help you channel the right voltages to the right paths. We already have standard test items complying with GBT. We can also have the smart DC to AC converters where there's CAN bus, right? Or it could be automotive, Ethernet, etc. We can still talk to the actual units. In some cases, they could be just static, where they take voltage, they have an output voltage, we make sure that it's within specifications, that's it. Some other cases, some manufacturers like to program their DC to AC converters, right? So it's still a universal input and you can program with different output while staying at the same power level. Or in some cases, the DC to AC converter needs to send status back to the OBC, right? So it could have CAN communication, it could have, again, automotive Ethernet, I2C, etc. So we have the ability to test through all those parameters and standards. Now, a typical test system for a DC to AC converter, again, we have a Mux box where you connect your DC to DC, you have your battery simulator. I have a battery simulator on both ends because it could be used as a battery simulator. Let's say it charges this way, this charges the other way, but it can also be used as a load or as a DC source, right? So you can take current, you can push current, and then on the other end, another battery simulator where you can take current or push current. Now, if we only have a one direction DC to AC converter, I would change the key components to an actual DC source, since it doesn't have to take current back, and a DC electronic load, which we also have available for your testing. Now, standard test, you have to measure the output voltage and current, noise, efficiency, overshoot, undershoot, input current, power, voltage ramp. So you want to, let's say, ramp it up to a certain voltage and see what's your range of operation, right? Because you can ramp it up, see when it turns on, you go through your envelope, and then where it shuts off if you're in an over voltage, input over voltage type situation. Line and load regulation, again, if we're, for example, this to AC converter is connected to your lights, right? So you have your running lights, it's going to be certain current. You turn on your driving lights, it's going to be a different current. You want to make sure that the output voltage stays within range. Power up, power down sequence, again, when it's turning on, so you can just ramp up, make sure that it turns on at a certain level. It shuts off if it's out of specification at the low or high level. Timing, how long it takes to turn on, to shut off if it loses power, and all the different protections, short circuit, OVP, UVP, overcurrent protection, overpower protection. So these are the DC to AC converters. Again, to summarize, one direction, two direction, they could be static, they could be smart, where you have communication. And again, it depends. These systems and these projects are custom to your needs. The next topic that we're overviewing is the battery management system, right? The battery management system, it, like its name says, it manages the battery pack. It is typically capable of measuring the battery cell voltages, just to prevent abnormal conditions such as overcharge, undercharge, over temperature, if you lose communication, etc. Most of the functions that a typical BMS has is voltage, communication, a state of charge, a state of health, abnormal warnings for any of the cells or modules, and protection. If you have a passive or active equalization of the batteries, right? If it's going into an over temperature type condition, current measurements, and some of them also have diagnostic tool simulation. So as you can see, basically on the left-hand side, we have a BMS, and it both charges and discharges or equalizes all the battery cells, right? The way that we help you test your BMS, you have the actual BMS, we have a high precision DC source going into it for a reference voltage, and then we can simulate as many cells as you want. That instrument allows you to test and simulate your cells in series and in parallel for higher voltage, higher current. Because as you know, when you start with your cells, you put them in series to reach a certain voltage, and from there you start paralleling to get to a certain current. With our cell simulators, we have the same ability to do that. On top of the actual hardware simulation, we have communication, right? Again, let's say that the BMS is measuring certain voltage at a certain cell, right? We already have a cell simulator there, and if they're different, you can go back to the BMS and recalibrate your BMS measurement, for example. Or if you want to read a serial number, if you want to read a code, if you want to get a temperature measurement, we can simulate that on the outside, force it into the BMS, double check it with the communication, and then go back and close the loop, right? Again, this could be for design verification, full production testing, R&D. It could be in a real-time environment, etc. Now, the key system features, like I mentioned, it's a high precision DC source, just set a reference voltage to your BMS, and the battery cell simulator. It depends on the number of channels that you want to simulate at some point. And then we have ancillary items. Again, it's going to be probably a BMM if you have any TTL controls, if you have any TTL outputs for warnings, etc. It depends on the type of communication that you have. Again, USB, Ethernet, EtherCAT, automotive Ethernet, I2C, etc. We can CAN bus. We can handle most of them. Some of the standard tests that we have on this test system, we can do a cell voltage simulation in series. We can help you with active and passive balance, right? Again, we start unbalancing all the cells, and we want to make sure that the BMS equalizes and corrects what we're trying to make it fail in a way. We have resistance measurements just to make sure that after they're connected, you don't have any difference in resistance between the battery cells. We can do a burn-in on the IC for the BMS. Again, it could be revision, temperature measurements, voltage measurements, etc., balancing functions, and protecting punch. So that's basically what a BMS test system is all about. Again, it's just two main components, and then we have ancillary components, which is software, communication protocols, and standards that you can test around. Again, the BMS, it's typically custom, customer to customer. As most of you know, on the electric vehicle world, the battery is just a power source, right? But the BMS and the intelligence inside the BMS communicating back to your car, that's typically proprietary IP. So that's where we work really closely with our customers to help them understand what we can do, for us to understand what they're trying to accomplish, and find the right testing protocol and procedure for it. Now, finally, we got to the battery, right? As everyone knows, as soon as you start talking about an electric vehicle, first thing that comes into mind is battery, right? So it starts with a battery pack, which is what drives the car. Then inside of it, you have your smaller packs or a module, and then it goes down to a cell, right? Our testers are designed to meet requirements in today's market as far as voltage, current, power, right? We also have the ability to help you with any driving simulation by an EVSE or FUDS, that it's two standards out there, and you want to make sure that instead of using an actual battery, right, we can simulate the battery while it's being driven. So you accelerate, your battery goes down, you start braking, battery voltage and power goes up. So we can simulate all those different waveforms. We can either have them on a real-time environment. We can, if you already have captured that data, you can put it into an Excel spreadsheet and then send that out to any of these units. All of them are regen. So when we're charging, obviously we take power from the grid to charge battery module cells. And when they discharge, it puts the power back onto the grid. I have an asterisk on the cell tester. You don't want to have a regen design on low power cell. Let's say we're talking about 50 or 100 watts, even if you have 16 channels, that's only 160 watts to put back onto the grid. It doesn't necessarily help you in any way, and it just increases the cost of the equipment. When we get into multi channels and high power, let's say 100 amp cells, right? That's when you want to put the power back onto the grid when you're discharging. For the module and the cell testers, those are multi-channels. The pack testers, they're typically 1 or 2 channel. Now, one technology that we have on all of our battery testers and simulators is that if you're charging on one channel and discharging on the other, instead of taking power from the grid and then putting power back to the grid, we cycle back into from one channel to another. Let's say from channel 1 to channel 2. Again, if both of them are charging, obviously we're going to take power from the grid, charge. If both of them are discharging, they go back onto the grid, or they can loop from channel to channel. And that's done automatically. You don't have to do anything during your test or simulation. For our cell testers, what's important to highlight here is that we have 3 voltage ranges. Multi-voltage ranges, or 3 voltage ranges. We can go from 0 volts to 10 volts. We can go from -5 to 5, or 0 to 5 volts, right? And you can see the accuracy on each one. We also have different constant current modes and ranges for each one on CC mode and CV mode. So you can really accurately program down into the microamps with our accuracy and precision on our instruments. Again, we have multiple models of cell testers at different voltages, different currents. If you're testing cells or you're looking to simulate cells, just give us a call and we can help you place you in the right test system or cell tester. Now, like I was mentioning before, we have a dynamic driving profile simulation, and this is for all the testers, right? Because you have the car going up the hill, down the hill, braking, stopping at a light, then you accelerate quickly up the light, then you stop again, you turn right. All that goes back to the battery, and it's a specific drive cycle simulation. When you do that, it could be at the pack level, then it could be at the module level, or it could be at the cell level, how everything goes upstream or downstream, right? These type of profiles are irregular, right? And typically we go into a dynamic current mode, which is basically a waveform. And the transition time from maximum discharge to charge, it's only 2 milliseconds. So we can quickly go from a full discharge to a charge in a very small amount of time. The test steps can be specified in an Excel file, right? We can have up to 720,000 data points, right? And the interval for the profile changes, it could be between 1 millisecond up to 10 seconds. So that's also programmable. Again, if you're looking into a real-time type testing environment, we also have the ability to help you with that. Whether you just want to do a play a recorded waveform, or if you want to close the loop, we also have the ability to help you with that. Again, the capabilities vary between the pack tester, module tester, and cell tester. So just drop us a line, drop us a question. We can help you and give you more information regarding those modules. Now, we have a dual mode of operation, which in reality could be 4 different modes of operation. We could be a tester, where we're testing the actual EV battery, and we run through a charge and discharge profile. We do a DCIR test, capacity, etc. Or we can simulate the actual battery pack. And again, it's the same. It's going to be the same equipment that you're using. It's just a different software platform, whether you're running through your recipe or you do an actual battery simulation. So it can help you both with your battery development as well as your battery testing. Another way that you can use these products, as we call it charge and discharge, it's also a source and a load, and it's a regen load. So again, you can just go into constant current. You just want, let's say, 25 amps in constant current mode. We'll be drawing that current, put it back onto the grid. Or if you just want to use it as a straight up DC source, we also have the ability to do that on a constant voltage mode or constant current mode. Now, staying in the topic of batteries, and in this case, we're going into the safety side, right? We have the ability to help you have your car being safe on electric vehicles and hybrids. You have a battery, you have a chassis. The chassis is conductive. You don't want to touch the car and get shocked, right? Or you don't want to touch any conductive metal pieces inside your car and get shocked, whether it's being driven, static, service, etc. So we have the ability to help you with hypot testing, LCR meters, have milliometers, and that's on the car level, also to make sure that your pack is safe, that your DC to DC converter, your onboard charger, etc. All the components that I talked about before, they also require electrical safety testing. Okay, but now the 2 topics that I want to address right now, it's a battery cell insulation tester and the battery cell surge tester. The cell insulation tester is an instrument used for measuring leakage current and insulation resistor of a battery jelly roll or dry cell, as well as some other insulation materials. Let's just stick to those 2. Besides the standard LC and IR, which is leakage current and internal resistance measurement, insulation resistance, we also have a unique function called partial discharge or flashover that may have occurred inside the insulation material during the high voltage insulation testing process. So what does this mean? You have a cell. Grab your hypot, right? A lot of us have worked with hypot. You test your cell, it passes. You know what? It's fine. I'm able to use it into my stack, into my module. Then it goes from the module to the pack. We're good. Well, with partial discharge, we can look at the battery's internal status before the electrolyte filling, right? So we can look at defective products, and they can be filtered out before entering the next stage of the production, preventing potential hazards that may occur in the field. We never want a product going out on the field and then have an issue. No one wants that. Instead, in contrast to traditional methods, we provide a new concept for inspection and evaluation of the battery quality. And I'm just going to go in depth, well, not in depth, but just at a deeper level on what we mean by partial discharge and all that. The other one is our battery cell surge tester, which is designed to test the insulation quality between the positive and negative plates of a lead-acid battery cell, right? Basically, what we do is we apply a high voltage surge impulse before the electrolyte injection process, right? Effectively decreasing the defective rates in production, right? We've given this product an output voltage that can go up to 6 kilovolts, right? It has a 4 thermal measurement and a sampling rate of 2 megahertz. So again, I'm going to go in depth into all the different modes and testing methods that these products have, especially for the cell tester. We have a couple of other applications that are not pertinent to this webinar. But the first thing that I want to talk about is the features on the battery insulation tester, right? We're trying to avoid safety issues, right? And you can see on the upper left hand all the different chemistries, right? How they act, and the safety issues on figure 3, which is it could be a metal particle between the anode and cathode. So the consequences, it could be a fire or an explosion from a lithium-ion battery, right? And that's a concern. I think we've all seen the videos, right? And as the cells move forward in their technology, also the energy density increases as well, right? Now, in order to eliminate the risk of a fire or explosion, the root cause must be resolved, and you need to make sure that any defective units are filtered out, right? How do we do that? Typically, an internal short circuit between the positive electrode, which is aluminum, and the material coated on the negative electrode, which is the anode, inside the cell is typically the root cause for a fire or explosion. Again, I'm referring to the figure 2. The burst on the metal electrodes or any contaminated particles inside the separator can cause this kind of internal short circuit. Again, just as a reference, look at figure number 3. Typically without the standard methods of testing right now, you cannot detect these issues, right? Our research also shows that the material coated on the negative electrode, it's typically graphite, would expand during the charging phase, expanding up to 24% or more as the charge and discharge cycle repeats, right? So basically, it'll continue to expand until the burst on the aluminum plate finally touch the graphite on the negative electrode, and you just have a fire, right? Or a small explosion. And that's how it's going to be happening on figure number 4, right? An example of 2 defective cells are presented on the production line. That's figure 5, right? And each one has a single burr with different height or length on its plate. You can see case 1 and 2. Case 1 will be detected at the second charging cycle when you're running your test, since the burr touches the anode then. But in most cases, the second one will not be detected until you go into further charging cycles into your process, which is very likely to happen when it reaches the customer. So, typical safety case, a safety test can catch case number 1. You typically never get to case number 2 until it reaches its final state on the product line, right? Now, we also have power discharge detection and a measurement function. There are 2 different phases in this case, and we have 2 different circuitries. The first one is constant current, where we charge the actual cell with a constant current, and you can set the current by your cell's capability. During this mode, we will monitor any voltage levels and slopes. Any glitches on those slopes or any unexpected changes on the slope will be detected and reported as partial discharge currents. The second one is constant voltage. Right? In that mode, we're looking at a stable leakage current during that test. So any unusual pulses on the current waveform are typically resolved or our normal discharge, which is a partial discharge or a flashover will where it will be reported back to your test. So you can see the constant current, right? You can see the partial discharge. You can see the leakage current measurement. Same thing, we're on a constant voltage mode. We can see the leakage current and the actual pulse with our product, which is the model number, if you want to know about it, is the 11210 Now for the battery search tester. The search test applies a non-destructive, short period, low energy impulse voltage on a lead acid battery cell, right? Typically when you do a high pot test, it's considered a destructive test because it wears down the insulation every time you apply it. So if you do high pot 5-6 times on a product, most likely it's going to fail at some point. In this case, we're just applying a quick search test, which is a low energy pulse. One thing that we do, the lead acid battery cell resonates with the internal inductor because there's, I'm sorry, I messed up on my notes here. Based on the internal inductor, it'll tell you whether it's a good cell or not, right? So we have the applied impulse, right? So we basically turn on, we have the impulse, and then we have the energy decay curve that that will be the actual impulse that we're going to be testing every single time. Again, we're going to be testing between the positive and negative, which is the insulation that we're testing, making sure whether the separator between the both of them are not short. Also, this is detected before the electrolyte injection, so it can reduce your effective production rates. Now, we have a pass-fail or judgment type test here. We have 8 different types of tests for the battery cell search. One is going to be the area, which basically compares the difference between the actual pulse and the total area between the waveform and the sample waveform, right? The next one is going to be the differential area, again, between the area created between the test waveform and the sample waveform. So you're going to have a golden waveform for a known good unit. That's going to be your template. And then you're going to be comparing it to the actual test waveform. On the first one, we could see the difference between a short battery cell and a moist battery cell, and that's for the area. Then we have, moving to the right, the differential area. Then we have a flutter where you lose contact during the test, and it'll give you a little flutter on the test, which is the total value of the waveform that is calculated. Then we have a Laplacian type test, which is calculating the second derivative of differential equation. You can check the occurrence of a small discharge. You can also detect rapid changes in the test waveform caused by the small discharge during a search test. Then we have B1 and B3, and those are the first and third peaks of a resonant waveform. Again, you have you have an expected waveform, and then you have the actual waveform, and we can just compare V1, V3. We can look at a Laplace equation. We can also look at the differential area, etc. And this is all already included in the tester. We can also look at the peak ratio. So we look at the actual peak on all the different resonances versus the template, and it'll tell you whether you're in range or not. Then we can do the actual peak or at the delta peak ratio in percentage. So let's say that you want it to be within 1% or 0.5%. So we just change our calculation and it shows you whether you're within range or not. Again, just to summarize, these electrical safety test systems, we start again from the overall car and the EVSE. We can help you to make sure that the charger is electrically safe, the car, then each of the components, down to the battery, down to the modules, down to the cell, down to the internal components of the cell and its chemistry. Now, software. I just glossed over software throughout all of our test systems. And the reason that I glossed over them is that we have functional platforms where you can just run your scripts and make sure that they meet all the criteria. And it's just a mass production type test. Then we have R&D, where you want to have a real-time simulation type environment where you want a closed loop. And if something changes on your BMS or your battery or the car, you want to make sure that it all goes back along with communication. We also have the ability to help you with that. We have battery simulation software, cell simulation software. We have battery charge and discharge to be able to run all your profiles. If you want to do a design verification test where you want to test all the different boundaries of a certain test, for example, efficiency, you want to test, let's say, the OVC at low line, and low line could be, 90 volts to 120 volts, right? And you want to sweep that range and then look at the efficiency throughout that range. And then you can also sweep the actual current capacity, right? So you sweep both of them and you can see how your efficiency is at different input voltage, different currents. We can change the actual communication on your unit. We can enter any defects, errors, protection circuitry, etc. So if you want to know a little bit more about any of our softwares, again, you can go to our chat. We already had a webinar on PowerPro, which is one of our main functional test system software platforms. You can go back and look at it. I believe we've done a webinar on our battery charge and discharge test systems. The software is called PowerPro. Again, you can look at that one. And most of our seminars are about an hour long, like this one. So you can just go back, look at them. Again, if you have any questions, you have any comments, you can just drop them in the chat. If you want to just send us information, specifications, test procedures, or just have a general questions, you can always send it to our sales team, which most of us are very technical. And the email address is sales@chromausa.com. Or you can just send me an email directly, which is my first name, last initial @chromausa.com. Again, I want to thank you all for attending. There are so many items regarding each application software that I did not have time to include them. Because as you know, once you go into, let's say, OBC testing, I mean, the depth of that application, it can take us 25 to 30 minutes. And then if we go into EVSE testing or simulation, same thing. It could take us about 15, 20 minutes just on that. And then we start talking about different standards. We start talking about different levels of testing, integration, software capability, etc. So what I wanted to do is just give you a quick 1 hour overview of all of our solutions. And then our next weekly webinar is going to go in depth into different applications, and that's going to happen on the next 3 weeks. So please continue on the chat room and let us know if there's anything specific that you require that wasn't covered in this webinar, or if more information is required. Again, thank you for your attendance, and I'll leave the chat open for about 10 minutes until we get all your questions. And again, thank you.